Ions are part of ionic compounds, so let's spend some time talking about ions and how they're formed specifically. So again, when we go to these electron configurations of compounds, what makes a compound a compound, one of the reasons why we like electron configurations is that I can find a favorable pairing by looking at what would work out for two atoms to end up with, in a compound structure, electron configurations that represent a noble gas. We call them a complete valence shell. So if it has a something S2 something P6, that's all 8 valence electrons, and it may or may not have some d electrons at the level just below the valence shell, but those things are participating in bonding. So I'm looking for situations where that would happen. Again, the main two reasons we tend to see are if I have two nonmetals having a very high electron affinity, a very strong pull on another atom's electrons, and an ability to maybe pull very strongly on them. Because they both have strong pulls, they kind of compete for a pair of electrons, and we say they share a pair of electrons to complete a valence electron configuration. So each one ends up with we have two nonmetal atoms attaining noble gas electron configurations. And it didn't really gain any, but because they both count that shared pair as being two electrons of their own, they end up having the effect of having gained electrons, even though there was no actual gain. We also have, when we have a nonmetal of high electron affinity, again, strong pull, but when it arrives near a metal which has a relatively low electron affinity and can't quite pull on its own or another more electrons as strongly as that nonmetal can, the nonmetal can take the electrons away and form a negative ion, leaving the metal as a positive ion. And so in those cases, the ions are formed in such a way that the metal loses all of its valence electrons and has none, but then that redefines what the valence shell is to be the shell below, which is full. And the nonmetals gain enough electrons through this process to have a full 8 valence. So both end up with complete valence shells. We refer to that as the octet rule. So in chemical bonding, atoms are going to transfer or share electrons in order to obtain outer shells of 8 electrons, 8 being a word, octet meaning 8, referring to 8 electrons. And this applies to all main group elements. So groups 1 and 2 and groups 13 through 18. The ones in the middle, 3 through 12, are not main group elements. So this is only those outer ones, and it applies to all of them are going to follow the octet rule except things in period 1. So that's going to mean hydrogen, helium, and then of course lithium and beryllium as metals. When they participate in ionic bonding and lose electrons, they're going to behave more like that first period row, and they're trying to achieve a duet of 2 electrons because period 1 would be full with just 2 electrons. So, So non-transition elements, it gets a little bit, so we can determine from the group what that charge of ion is going to form, because we know when it's done forming, it's going to have a complete octet shell. So for these low electronegativity metals, they're going to always lose electrons. All metals are going to lose electrons when they form ions and form cations. They'll never form an anion. So group 1 elements are going to form +1 cations. Group 2 elements are going to form +2 cations. Meanwhile, the high electronegativity, high electron affinity nonmetals, this is groups 13 through 18 nonmetals, are going to gain enough electrons to end up with 8. So group 17 will make -1 ions, group 16 will make -2 ions, group 15 will make -3 ions, group 14 will make -4 ions, and pay close attention to the fact that I've underlined nonmetals. So things below the staircase in groups 14, 15, 16, they will not form anions. They're metals, so they'll form cations. So only talking about the nonmetals. This becomes very important. You need to memorize this and be able to predict the charge of an ion for a main group element based off of where it sits in the periodic table. Transition metals in that these non-main groups, we call that groups 3 through 12, are going to lose electrons because they're all metals, but not in such a predictable pattern. It is complicated because they do have valence electrons, but they also have non-valence d electrons that are pretty far out and sometimes get lost and sometimes don't. And so what we have just done is observed the patterns and have to memorize the charges that they can make. This is on your memorized stuff list, so you need to be memorizing these charges. Note that some of them, like silver and zinc and gallium, only make one particular ion. So silver only forms a +1 cation, gallium only forms a +3 cation, but we see some of these other ones can form multiple charges. So sometimes tin, Sn, forms a +2 and sometimes it forms a +4. In order to distinguish those ions, because they will behave differently, they have different charges, I will use Roman numerals after the chemical name after the element name to indicate which one. So tin, parentheses, Roman numeral 2 means tin with a +2 charge ion. And tin with a Roman numeral 4 means tin with a +4 charge ion. And so that's how we're going to designate which of these we mean when a metal is capable of having more than one possible ion. Here's another visual of it, of kind of showing these common cations and anions in a table. And you need to be working on it. The memorized list is the one I had on the slide before. It's also the one in the memorized stuff list. So hydrogen, as usual, as always, is always going to kind of be weird. It doesn't quite follow patterns. It is a nonmetal, even though it is to the left of the staircase. It is considered a nonmetal. We've already talked about that. And sometimes it makes cations, +1 ions. Sometimes it makes anions, -1 ions. So it kind of depends on the situation. It can form ionic bonds. When it does, it's usually it would then be a positive charge. It can also form ionic bonds with metals sometimes and take on the -1 charge. It can form not covalent bonds. Primarily though, where we are going to see a lot of hydrogen is when it shows up as an acid. Acids are covalent compounds of hydrogen with other nonmetals, but the hydrogen is written first and they're very complicated and we really aren't going to get into them too much in 121. So we're just going to identify them by chemical formulas that begin with an H in chemical formula form, or if it's a name, it will include the word acid in the name. And so those are considered covalent compounds, but they're most primarily considered acids. So they kind of have their own system all amongst themselves. We also can sort of now, to determine some of these bonding patterns, we can use something called a Lewis structure for an atom. And this Lewis structure is going to basically only show the valence electrons. So I can see it as a neutral atom. I can also see it after it's gained or lost electrons, and sort of see what's going on with it. So again, oxygen has 6 valence electrons. So 2 is the highest occupied level, so it would be the valence shell. And I have 2 in the S and 4 in the P, so that's a total of 6 valence electrons. Also, it's in group 16, which means it's got 6 valence electrons. If I draw the Lewis structure, I draw 6 dots representing those 6 valence electrons. And I'm going to draw them in such a way that I put 1 dot on each side, and then I come back and fill up. Kind of like when doing an orbital diagram, I put 1 arrow up, and then I come back and put a second arrow down. Little bit different because we would put for the S orbital, we put up and then down, and then for the P orbitals, we put up, 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 down, down, down. Slightly different, but we'll just put out 1 at a time. So if I did that for all main group elements, I have 8 possibilities for how much valence they have, 1 through 8. And I can see the different Lewis structures I would get using representative atoms from each of those 8 groups. Group 1 would be like lithium with 1 dot. Group 2 would be 2 dots. Group 3 is 3 dots. Group 13 is 3 dots. 14, 4 dots. 15, 5 dots, etc. And we see that these are then going to have all, once they complete, if they form ions, they're going to end up with 8 valence electrons. The metals down here are going to lose all their valence electrons and have none. The nonmetals up here are going to gain enough electrons till they have all 8. So for helium, again, those 4 sides represent the 4 valence orbitals. And since there's only 1 valence orbital, I really should show for hydrogen and helium, I should show both electrons together on one side, only for the first side. Once I get to the next sides, I really should be doing one at a time. Honestly, I'm happy if you were to show two separate dots on different sides. We can use these to show electrons being transferred, and from that I can kind of make predictions about what's happening. For instance, potassium is group 1. I know it makes a +1 cation, and I can see when it transfers and loses this one electron, it's going to have a +1 charge and no dots. Chlorine has 7 valence. It needs to get 8. It needs one more. It's going to take that one from chlorine, so I can see that the potassium can transfer it to chlorine, and now chlorine has 8, but it also has gained an electron, so it has a -1 charge. Notice that the charges cancel each other out. I end up with a neutral compound. This is a compound because I have a positive ion next to a negative ion. It's implied that they are ionically bonded. I also see that the charges cancel. This is one way of doing a structural formula for an ionic compound. We could do it for something like magnesium oxide. Again, magnesium is a metal, oxygen is a nonmetal. I'm expecting to see an ionic pairing on this, and I expect to see the magnesium to lose electrons and the oxygen to gain. So I can figure out their valences and draw the dot structures of just the atoms. Magnesium with 2 and oxygen with 6. And then when I see this ionic bond, I see that magnesium is going to transfer its 2 valence electrons over to O. They go to different locations. I've circled them with red just so you can kind of see where they ended up. However, once it transfers, it no longer is neutral. It now has a +2 charge. Once oxygen has received those 2, it no longer is neutral. It has a -2 charge. So it's like this is the atoms up here before bonding, and after bonding, I can see this is my final ionic structure. In this case, again, it shows a neutral compound because +2 cancels -2. I know it's a compound because it's positive ions right next to negative ions, and I can tell that that's implying that there's an ionic bond. So this is one way I could figure out the compound Lewis ionic chemical structures. I could look at these and determine, okay, sodium needs to lose 1 because it's a metal. Sulfur has 6, it needs to gain 2 to get its 8. But I see that that's not going to quite work. So if I transfer 1 from the sodium over to the sulfur, sodium's happy with the +1 charge, but the sulfur needs 1 more electron. So I get another sodium atom to supply that last electron. And so I can see this would be the structure where it'd be canceled out. I have 2 positive charges, 1 -2 charge, that cancels each other out. So that means that the proper chemical formula for a neutral ionic compound would be Na2S. I need 2 sodiums to complete the octets for the sulfur. So just to recap, when I try and figure out if it's an ionic compound, does it have a metal? Oops, lost the AL. Does it have a metal? If yes, then it is, because metals can only form cations and make ionic compounds. They can't do any sharing of electrons, can't form covalent bonds. Does it have a polyatomic ion? Maybe it only has polyatomic ions in it, like ammonium NH4 is not metals, but it is a polyatomic ion. Ions mean that it's an ionic compound. So yes, as long as it doesn't begin with hydrogen, that's a little bit tricky. If it does begin with hydrogen, then it is covalently bonded and considered an acid. It's both an acid and covalently bonded. So I would kind of, if it was asking ionic or covalent, I would classify it as covalent. If it was asking ionic covalent acid, I would classify it as an acid. So if it only has only has nonmetals, and there are no polyatomic ion formulas in it, then it's covalent.